So, welcome back. In the last lecture, we learnt about reflection and refraction, etc., at a single boundary. Okay. Today, we'll take the case of a constraint where both the ends of the vibrating body, whether it is a stretched string or it is a pipe where the vibration may take place, if the both ends of the pipe are closed. Okay, and this is also true in case I have a rod which is clamped in the middle. The rod is clamped in the middle and it is made to vibrate. Then this end is a free end and this end is also a free end. So that kind of vibrations are there. And similarly, in the case of an organ pipe, we can have both the ends of the pipe. It has been shown to be closed here, but they can be open. Okay. So there is a symmetry, and we'll talk about that. I have not made either a pulse or a wave or anything, but I have just shown over here that there is a stretched string of length L. The string has got the same linear density all over, so that the velocity all over is the same, because the velocity is given by tension upon the mu under root. Okay. Similarly here, I consider that whatever are the contents of whatever kind of a gas is there in this pipe of length L at a given temperature and pressure and having a certain velocity due to the pressure and the density content, etc. Now you know all those things which are required for the propagation of a longitudinal wave, if it is there. Now what we are going to study in this case is that there are two reflecting surfaces, two rigid bodies, between that the string is stretched and then some kind of vibrations are made to move on the string. How come? I leave it to you, and I will tell you also later on. But there is one wave which is traveling in the positive x direction and the other one in the negative x direction. Okay, just opposite to each other. In this case also there are two waves, one is traveling down, the other is traveling up. Okay, or if I keep the pipe like this, to the left and to the right, all those things, they don't matter at all. Now we have some certain conditions that the waves which we are talking about, they have the same lambda, they have the same t, they have the same nu, they have the same velocity, and they have the same medium. Okay, under all these conditions we obtain what are the standing waves. And there is a question sign. Why there is a question sign? I am asking you, are they waves? And you will say they are not waves, they are basically vibrations. But in physics, historically we call them standing waves or stationary waves and never call them vibrations. So we stand by our history, but we have to tell you that they are not waves, they are oscillations. Okay. So standing oscillations or stationary oscillations is another name for this thing. Okay. And we are going to find out as to what is the normal mode of vibration in this case. Well, what happens is that after some time, it may be very small, once the vibrations are there. Okay, now I told you that how come these vibrations can be created. So for example, if this is a stretched string of a sitar, guitar, etc. What I can do is I can pluck it in the middle here. I can pluck it as I like. A small pluck or not. But if you take a sitar guitar and you try to pluck here or here at the two ends, then there shall be no vibrations. Of course, I'll tell you that there will be something called antinote which will be created over here, and what are the places where the sitar or the guitar or a string can be disturbed. Okay. But after some time, a steady state pattern is set up. Okay. Now the waves start, they are moving left to right and right to left, and this is from left to right, okay, in the positive x direction, y1, and in the negative x direction, that's y2x comma t, and then they superpose. On the left hand side will appear a drawing which will show you how the two waves, one going like this and the other exactly opposite in phase, they superpose and a steady state pattern is set up. I find myself incompetent to produce that kind of diagram, okay, because of my own constraints. So please look at that, and I'm not going to explain it to you. I rather ask you to ponder over it, to look at it, to see what is happening, question yourself, satisfy yourself by your answer, and you are a learned person. And you are. Okay? So I have two equations. One for the wave traveling in the positive x direction, and the other for the wave traveling in the negative x direction. This I have shown negative x, and this is the positive x. And similarly we can have waves traveling in one direction and the other direction over here. I am not indulging in that part right now. So what happens? Both the waves are there. Hello brother, hello sister, and they superpose. When the superposition occurs, then we get a net disturbance. Yx comma t is equal to y1 plus y2x comma t. So I can write this as an equation like this. Okay. Sine of kx minus omega t, sine of kx plus omega t. Which, because of the identity which we have discussed earlier, sine of a minus b plus sine of a plus b is equal to 2 sine a cos b. Even the students who are not having a mathematical backup, they can split it and find that this is equal to 2 sine a cos b. Okay. Because this is equal to sine a cos b minus cos a sin b, and this is equal to sine a sin b cos b plus cos a sin b. So it turns out to be equal to 2 sine a cos b. So I write this as, okay, this plus this gives you 2kx divided by 2, and I get 2a sine of kx cos of omega t. Now this part it depends upon the value of x, and cos of omega t says that whatever be the value of 2a sine of kx, all the particles are vibrating with a phase equal to omega t. Okay? So I say that the equation turns out to be y is equal to 2a sine of kx omega t. I have taken this in bracket, which means the amplitude over here is varying as the value of which x changes, but the phase cos of omega t, this defines that all particles or portions or small elements of this string they are vibrating in the same phase. Okay. Now to analyze, the equation doesn't tell us anything unless we analyze this equation. What we do, we take this part, 2a sine of kx, and say set the value to be equal to 0. When this value is 0, then we get nodes. Okay. Then we get nodes. And if we get 2a sine of kx is equal to 2a, that is, this is equal to 1, sine of kx is equal to 1, then we get what are called the antinodes, where the value of the amplitude is optimum maximum, and here the value of the amplitude is minimum, which is equal to 0. So that means that all waves cannot travel inside the pipe, are all waves of all frequencies, any frequency for that matter. If you say that any arbitrary frequency, no. Certain fixed frequencies are there. The possible wavelength is constrained. That means it has got certain fixed values. Okay. Not arbitrary. And the lambda, the wavelength, is a function of the length of the stress string or the length of the pipe. Okay, we have taken as a no matter. So in the first instance for the nodes, I put sine of kx is equal to 0 and then solve it. I find that if sine of kx is equal to 0, then kx must be equal to n into pi. Well, what is n? N is equal to 0, 1, 2, 3, 4, 5, 6, like that, integer. Putting the value of k over here, 2 pi upon lambda into x is equal to n pi, I get the value of x as n lambda by 2. Okay, n lambda by 2, where n is equal to 0, 1, 2, 3, 4, like that. Similarly, in this case we can say, of course you have to understand that the deflections are at both sides, both ends of the stress string, or in the case of a pipe which is closed. So for the other situation, sine of kx, and we are taking the mod of it, okay, is equal to 1, because sine of kx can take values, maximum values, as plus and minus 1. We are just taking this. And then kx should be equal to n plus half to pi, which means n pi plus pi by 2. n pi plus pi by 2. Okay. For n pi, because n is 1, 1, 2, 3, 4, 0, 1, 2, 3, 4. Therefore, n phi, the value should be equal to 0, like before in the case of node. When pi by 2 is added, so I get the value of kx, sine of kx as equal to 1. Okay. So I can write from this equation, I come to this equation, 2 pi upon lambda into x is equal to n plus half into pi. Okay. We'll write it as half, 1 by 2. We'll never write it as 0.5. I will be called an idiot, and so will you be. Okay? Because this doesn't help. Let it be 1 by 2. Okay? A fraction. So from this equation, I can write x is equal to pi, and pi will cancel. So lambda will come here and 2 will come here, and lambda by 2, n plus half. Let's substitute the value of n is equal to 0. So I get what? Lambda by 4. I substitute the value 1 over here, so this becomes 3 by 2, so it becomes 3 lambda by 4. Okay. Next, 5 lambda by 4, which is odd into lambda by 4. Okay. In the previous case, when sine of kx was equal to 0, we got these values as 0, lambda by 2, 2 lambda by 2, like that. Okay. So that I can write as even into lambda by 4. Okay. So even numbers into lambda by 4. And if we try to find the distance between consecutive nodes, one node and the next node, there may be many nodes. So what I write for n, I write n plus 1 into lambda by 2 minus n lambda by 2 becomes equal to lambda by 2. Right? And similarly, I can work out the consecutive antinodes, the distance between them. This will also turn out to be the same lambda by 2. So node to node, antinode to antinode, which are neighbors to each other. Okay, like that. So I can write. Now let's see. I have this as L or this as L. Okay. The confines of the system is that I can write L is equal to n into lambda by 2. Okay. For the nodes. And similarly I can have for antinodes, etc. So when I take the length n into lambda by 2, when n is equal to 1, 2, 3, n is equal to 0 has got no sense. I don't say n is equal to 0 is nonsense, but I am saying that n is equal to 0 has no sense. Okay. So we take n is equal to 1, 2, 3, etc. Now, I can write lambda is equal to 2L upon n, where n again 1, 2, 3, 4. Now, so I can write if n is equal to 1, okay, here, then lambda will become 2L. If n is equal to 2, then the corresponding lambda, which I can write lambda dash, just to distinguish it from that, will become 2L by 2, okay, 2L by 3, etc. Okay. Now, I have the master equation like a master bedroom in a house. What is that? In any wave, nu lambda is velocity. Okay. So I can make use of this and calculate the corresponding nu as velocity divided by lambda. So it will turn out to be equal to v divided by 2L. This is the fundamental frequency or the fundamental mode of vibration, the normal mode. Okay. If I double that, then we will get V for this case, V divided by 2L by 2. I didn't write it as L. L is again, now writing L over here is nonsense. And so I continue with that and we obtain the other frequency. Okay, this I can write as nu dash or something like that. This turns out to be 2 into V upon 2L. So we find that if the frequency to the fundamental mode of vibration is nu, then we get nu, 2 nu, 3 nu, 4 nu, like that. And we call them second harmonic, third harmonic, fourth harmonic, etc., etc. However, in the case of if you go and study music, physics of music or the masteries of music, then what we call the second harmonic, they call it first overtone. Third harmonic, second overtone. We study music. Okay? So after we have a discussion about both the ends closed or both the ends open, I'm going to take up the other thing where one end is closed and the other end is open. For example, here there is a rod of uniform density of a certain length L, okay, capital L, and this is clamped here, and the other end is free to move. We create the oscillations. So one of the things is that I can get a frequency like this, okay, or another case I've just shown to you is with the dotted red lines, where now I have a node, I have an antinode here, then again a node here, and then an antinode. Okay. Similarly, in the case of this pipe, where this is x is equal to 0, and there is a node because some water is filled over here, that is a reflecting medium. So I can have the antinode here and node here, and half the wave is created, fundamental wave, or a harmonic wave which has been shown by the red color, which starts with the node here, antinode, node, antinode, because they take place alternately. Well, I can write L is equal to n plus half into lambda by 2, picking up from the mathematics. So here n is taken as 0, 1, 2, 3, 4, okay, so there is no problem for a 0 here. So possible wavelengths are, I can write lambda is equal to 2L divided by n plus half. Okay, it's very simple. And you can scribble it faster than I can. So the fundamental frequency, I am just writing new one. This will be equal to the velocity divided by lambda, because the beauty equation is V is equal to nu lambda. Okay. So making use of that beauty, I can now write the fundamental frequency in terms of the velocity. Okay. And if n is equal to 0, then this turns out to be equal to half into lambda by 2, or lambda will turn out to be equal to 4L. Okay. So for the fundamental frequency, I have this value here. Okay. I have this value over here, V upon 4. The next possible thing is, when I take the value of n as equal to 1, so this will become 3 by 2. So my lambda becomes equal to 4 by 3 L. Okay. But this frequency naturally will be the third harmonic frequency. Okay. Then we have, in such cases where one side is clamped and the other side is open, or one side is closed and the other side is open, this will be, so only the odd multiples of the fundamental frequency, that is, if I have the fundamental frequency as nu, then 3 nu, 5 nu, etc. will be there. They are called, this is the third harmonic, but ask a musician, then third harmonic in this particular case is first overtone. Okay. So I have lambda here, and this is lambda by 3, this is lambda by 5, like that, odd harmonics. No even harmonics will be present. Okay. In the case of both sides clamped or both sides open, all possible harmonics are there. That is, we can have the frequencies nu, that is the fundamental frequency, 2 nu, 3 nu, 4 nu, etc. Okay. I am attached here, this point. There is a graph which is appearing, which is giving several harmonics and shows how the notes and antinodes are formed. Okay, you can have a look at that and you can further your studies all by yourself. Okay, so we have odd harmonics in this case and all harmonics in the case of and even and odd, both harmonics are possible in the case of when both the sides are clamped or both the sides are open. Okay, so this is what we have obtained. Now one interesting feature which I leave it to you is called the case of a force vibrations. In the case of the force vibrations we have resonance, and there is an experiment that we have a pipe is there, and we have a, what is called a fork. Okay, fork is there, and when I can change the position of this water in it, and when we bring it closer to it, then there will be harmonic frequencies and third harmonic frequency, etc. will be obtained with the help of that. This is called the tuning fork. Okay, tuning fork itself, you can see that it is like this. Okay, and here there is an antinode, and here also there is an antinode, and here of course there is a node. Okay, in between also you can have an antinode and a node, antinode and a node, and that way this tuning fork can give you the fundamental frequency or other frequencies. Okay, with the help of these two we find the speed of sound, okay, by making things there. So the next item is going to be the beats, where we'll talk about a packet of waves and how they behave, and that is also a very beautiful concept and particularly from the point of view of objective questions. So it has been good to have you here this lecture, and thank you very much. Okay, but today I would like to again point out to you that you question and we answer. Okay, and you can re-question and I can attempt another answer, and this is what I desire for this series of lectures. Thank you very much.